So in this last session, we're going to hear from the students of the graphical models group, and it's going to be a mix of both the work they have done in the summer and the things they're proposing for continued funding. At the end of this presentation, I'll do a short wrap-up. I know Jim Bass wants to address the audience and say a few things, and Charles Swain had said he would, but I don't see him here, so I don't know if he changed his mind. Oh, he's on the cell phone outside. Okay, so hopefully he'll be back in time for the conclusion. So let's start. Who's going to go first? Pangshu, go ahead.
Okay, first I want to apologize because my handout isn't exactly the same as my presentation, but the main point will be the same. So basically I want to talk about an iterative approach to discriminative structured learning. So during the workshop, we tried some discriminative structured learning procedure. Here's the outline of the procedure. First, we built baseline H&M system. Then we performed utility alignment of the training data. And based on that alignment, we performed bivariate mutual information computation. And then discriminative structure selection and some parameter estimation of the new model. But I think there are some problems with this procedure. First of all, the retrieval alignment may change after training a new model. Then, in the model training, with parameter estimation, we use MLE. And this might be, well, MLE is not discriminative. So, finally, retrieval approximation restricts the mutual information computation. We might want to weight all paths by their posterior probability. So for discriminative model learning, our goal is to minimize this quantity here, which is the divergence between the true posterior probability and the posterior probability according to our model. And this may suggest that we can do better with an iterative procedure. So here I present two possible improvements over the learning procedure we adopted during the workshop. So the first one is an iterative approach. So we can think of an EM-type iterative structure and parameter learning. It's not EM because haven't formulated as the EM algorithm. So it's the EM type. So in the E step, we perform the retrieval alignment of the training data and calculate the mutual information. And during the M step, we discriminatively we use the discriminative conditional mutual information and perform the DMM, which is the varied Markov model, edge selection, and modify the structure of the model, and then perform model parameter learning. We can use maximum likelihood, or we can use maximum MMI. And then we will repeat the procedure until the alignment stops changing. So the DMM structure at iteration n could be like this. And then after one iteration, it can be like this. And if you can notice, some of the edges may change and some will not change. So the second possible improvement would be the soft alignment of the training data. In the retrieval alignment, the label for each frame is deterministic, and the posterior probability of the label given the data is just a delta function. So if we can use a soft alignment where we compute the posterior probability using the forward-backward algorithm, then each data frame can contribute to all the labels. And this way we might have a more accurate mutual information computation, and the model from the previous iteration may influence the alignment more than in the Viterbi alignment. So based on the ideas, here's my proposal for the next year. I want to formulate the iterative model structure and the parameter learning, and then theoretically study of the EM-type learning procedure, and also try to implement the improved mutual information computation within the graphical model program, and finally apply the new learning procedure to different data sets, including Aurora, Audoviro, and so on. Yes?
You motivated the most of what you're proposing by saying that you wanted to minimize the divergence between a model and a desired distribution.
The true posterior distribution?
So the desired is the true posterior.
Yeah. Yeah.
Now, even if you have the Viterbi alignment, computing this mutual information with a fair bit of computation, right?
Yes.
You essentially chop up the training data into parts and you do separate calculations for each part, and then you average things over if you want a big Q or if you,
Right.
or you keep them separate if you want a little Q.
Right.
And that only took how much, a week or 3 days or whatever? Are there closed form solutions if you do the soft thing, or does this?
Yeah, there are closed form solutions.
So you work them out?
Yes, for the mutual information computation, yes.
Okay.
But yeah, the time is a big issue because for Aurora dataset, just calculate the mutual information will take about a day on 40 CPUs.
Because otherwise, between like a standard HMM training procedure, the difference between Viterbi and 4 factors is not a whole lot. Probably a factor of like 2 or 3. Right, so you're confident that this is also the same thing?
Well, this may require more than that, more time. But I don't know the exact time. So, yes.
Can you actually go through this the soft decision thing that you're proposing again?
So basically, in the bivariate mutual information computation, we first estimate for each pair joint Gaussian mixture distribution. And in doing that, we use the Viterbi alignment. So basically, we put the data pairs into a bucket and then estimate a Gaussian mixture model in that bucket. And here, we will not put the data pair into just one bucket. We'll put it according to the probability to all the possible buckets. Each bucket, I mean, for each.
I'm confused about whether you're talking about using soft decision for Gaussian clustering, or you're using soft decision for the BMM structure induction. But what are you talking about using soft decision for?
For the mutual information computation.
So how would you use it for the mutual information computation?
In the mutual information computation, we first estimate a Gaussian mixture model for each pair.
Oh, you're not doing it from the data.
It is estimated from the data.
So you get away because your mutual information calculation is based on a parametric model.
Yes.
And if you did Viterbi, you would like have some sufficient statistics for estimating those parameters of the parametric model from which you then get the mutual information by a formula. and the sufficient statistics you need for the viterbi alignment and those that you need for the soft alignment, they're very related. In one case, you have separate buckets and
Right.
restrict in one or the other. In the second case, you multiply by gamma. And
Right. Exactly.
So that's why this is not going to change the configuration. At most, increase it by a factor, which is maybe
It will change because
some fraction of the number of states, because a large number of probability that may be non-zero.
Because right now, for each label or for each cube, small cube, you will have to consider all the data points. But before, you only consider whichever falls into the bucket.
Well, the other way is probably better to look at it. For each data point, earlier it used to go into one bucket,
Right,
and now it may go into multiple buckets.
right, right.
You could probably approximate.
Yeah, we can use some beam and reduce the computation.
One other question, if you assume, so let's say that you're computing visual information assuming mixture of Gaussian parametric model for your joint density, is that a closed form solution for the visual information if you have a mixture? I mean, there's a closed form if you have a single component.
Right.
So you do it iteratively, or,
Yeah,
and it's binary, so it's just, okay.
yes.
I wish.
Yeah. and that is-
All right, thank you very much.
Okay, I'm Kevin Filali. I'll be talking about multivariate vector information for social learning in GeoSP. So I'll first talk about why multivariate vector information is useful, and that will be a recap of what Thomas said about variate and its limitation. Then I will show how mutual information is computed. Then talk about the main issue with computing the multivariate mutual information. And then end up with the ways to speed up multivariate mutual information calculation. So in this example, we have three possible parents for variable x, conditional state Q. And using our bivariate criterion, we found out that the discriminative mutual information of Z1 to Z2, 3 is in this order, Z1, Z2, Z3. So if we only had bivariate mutual information, and we want to have one link for one parent for variable x, then we go with Z1 because it has the highest discriminative mutual information. The problem is if you want to have more than one link, say you want to have two links, then the only information we have is that Z1 and Z2 have the highest discriminative mutual information, but that doesn't necessarily imply that Z1 and Z2 taken together have the highest mutual information. So that's the first reason why we need multivariate mutual information. Another example by Thomas actually is if you look at, say you have 8 bits and the parity bit, and then you wanted to find the mutual information between the parity bit and the subset of the other bits, you'll find no mutual information at all if you look at any subset less than 8. So you can find some pathological cases even in cases like this. The other problem that's related is you might have like Z2 and Z3 having high initial information, but basically one being dependent on the other and not adding anything new to discriminate the variable X. So this slide is basically just repeating what I showed in the example. We have two main problems that we can't look at the features alone, and we might have redundant initial information. So now I will talk about how initial information is computed. So this is the multivariate case, but it's very similar to the bivariate case too. So we start with our feature matrix, which is like the speech data. This is the features at each time frame. And then we have sliding window that selects at each time frame the features that we're interested in. So in this example, we're interested in this pants in red and this gray child. So we collect this data and we get it into this matrix, XY that extends also across time. And then from this, we model density using initial Gaussians. From this model, we sample vectors XY according to the distribution, and then compute the initial information using the law of large numbers. So we typically need to go to 10,000 samples or so. And yeah, and I'll talk later about how it's done in the bivariate case. It can be done this way, but it also can be done different. So the main issue with the multivariate initial information is that it's very expensive. So there are many more sets of files to consider than in the bivariate case. On top of that, we have these other problems with the higher dimension and with the EM algorithm taking longer to converge. And also, an important point is that some optimization that are used in the bivariate case are not possible in this case. Or they are hard to perform, or they're not really proven to do any good. For example, one such optimization is instead of calculating the initial information using the law of large numbers, is to use a grid to discretize the probability distribution, and then the calculation of initial information becomes very easy from that. And because in the multivariate case we have higher dimension, it's not clear that that will help us much unless we have a very dense grid. So we have shown that multivariate MI calculation is really important theoretically, and we avoid the problems we have with the bivariate case. But since the speed is really an issue, we might resort to some approximations like using cross-correlation instead of multivariate instead of feature information, or clustering algorithms. Another thing that I would like to investigate is finding whether there is any correlation at all between the number of EM iterations that are needed for convergence and the eventual MI value that's computed. So because we tend to have sets of features that take a very long time to converge, and we don't want to be spending time waiting for them if they're not going to give us a high initial information again. The other obvious thing is parallelization, and this is done also in the bivariate case, and both algorithms are very easy to parallelize because calculation of the initial information on different sets are completely independent. So just to conclude, the bivariate MI calculation has proven to be very useful when we have one link per child. We can also use heuristics to extend it to 2 links or 3 links, but it's unlikely that we can go higher than that without losing performance. Multivariate MI should likewise, if it's performed correctly, give us the same improvement that you got by doing bivariate MI in those ways. And then there is work that needs to be done to make multivariate information faster.
Okay. My name is Karen Levescu, and I'll be talking about articulatory modeling for speech recognition using the graphical modeling toolkit. This is something that we started working on during the workshop. We ran into a lot of memory usage problems. And so now that we have the log space algorithm for training, we can actually pursue this. So I'm hoping to pursue this next year. Okay. I'll start with giving some motivation for both why I think we should use articulatory models for speech recognition and why graphical models make sense as an implementation for modeling articulation. I'll go over an initial proposed model which we started building during the workshop. And I'll briefly touch on various issues like the choice of features, the model size, the initialization, and options for structural learning on the model. Okay, so why articulatory modeling? So I'll start with a definition. So what this picture shows is a cross-section of a person's head with sort of the main articulators pointed out. So there's the glottis, which is the opening between the vocal cords, the velum, which is the soft palate that controls how much air flows through the oral tract versus the nasal cavity, the tongue, which is actually a complex of articulators, really, because you can vary different parameters of the tongue, and then the lips. So articulatory features specify the state of each of these articulators, so like the tongue position, the lip opening, the velum degree of closure, things like that. And feature types that have been used are binary or multi-valued. So binary tend to be like the Chomsky and Halley type features. They can be discrete or continuous, and they can be a partial description which is used in conjunction with the phones, or they can be a complete description. And I'll mostly be concentrating on complete description. And there are a lot of motivations. There are a lot of bullets here. They're very related to each other. Basically, it can be summarized by saying that there's a lot of evidence to show that speech might be better represented by articulators moving asynchronously rather than phones that have a distinct start time and end time. When you look at a spectrogram, it becomes really clear that for a lot of phones, you have no idea where one stops and the other one begins. So it's a little bit artificial to say that there are actual phones there, that phone segments that are defined like that. You can use articulatory features to very concisely represent certain co-articulatory effects that take more trouble to represent with phones. So for example, vowel nasalization, which is just one feature changing. Another one which is one feature changing is stop closure insertion. So there are instances where it looks like you're inserting a stop, like in warmth, being pronounced as warmth. And I'll show a more detailed example of how that's described by articulation. Articulatory features can also help us to recover information. So if we see that a vowel is nasalized, but there doesn't appear to be anything following it, well, we say that vowel is nasalized, that probably was a deleted nasal. Whereas in a phone model, it's very hard to recover that information. And again, this is kind of related to pronunciation modeling, where if you have a pronunciation model that says this phone gets completely replaced by some other phone, it's very hard to tell what actually happened. The phone does not actually get replaced by another phone. It more likely gets modified. Okay, so now that I've beaten that to death, here's the example that I was talking about. So warmth to warmth. In the phone-based view of what happens, the brain, so suppose you're at the end of the word warmth. You're after the M, you're starting the th. And the brain says to the articulators, give me a th. And all of the articulators in the phone base where you go, okay, sure. And they all go to the th. Okay. What is more likely to happen, the brain says, give me a th. The velum and the glottis are probably pretty quick to respond. The tongue is a little bit slower, and the lips are just like off somewhere else. You know. So what the result of that is that it looks like there's another stop closure in there. So this is, I think, a much more concise way of describing it, rather than saying that there's a phone that actually gets inserted. Okay, so that was why articulatory modeling. Now, why graphical models to represent articulation? So again, I have a whole bunch of very related bullets. Basically, graphical models are a very concise way and a very transparent way of describing models where you naturally have a lot of variables that you want to describe. So you could collapse all of the articulators into one state, but then it's very difficult to say, to make statements about parts of that state. So there are statements that you want to make about only voicing or only nasalization, and then you either have to talk about parts of states or clusters of states, and it gets very clunky. And we can also, if we want to do structure learning, we can do structure learning on the particular variables of interest. And again, we have to sort of think about what state combinations correspond to that variable. And articulatory models use are a typical model with a large number of variable substates. So they would take advantage of these properties. Okay. So I'll show an initial version of a model that we implemented here at the workshop. And this is actually very similar to what Jeff Zweig had in his talk, just with a few more articulators and without the word and the word transition at the upper levels of the graph. So in this model, the articulators depend on the phone, and for each articulator also on its own previous value. There's no dependence on other articulators. And however, we would like to have, in light purple, I'm indicating things that haven't been done yet in the model. We would like to have these dependencies either between articulators in the same time frame or in a different time frame. And I'm hoping that these would be learned, because there are just too many of these links to put them all in by hand. And I spent some time thinking about it this summer. Couldn't imagine which links I would want to put in.
Clarification question. You have an arrow going from A1 to A2, and you just said...
That should not be there. That should be purple. Thank you. Yeah. Okay, so this is the initial model that we came up with, and the modifications that I'm hoping to make. I think I'll kind of skip over this because I'm running a little bit late. Basically, this is supposed to show just how easy it is to specify an articulatory model in GMTK. So it's very easy. Okay. Some issues in articulatory modeling. So first, you have to decide on your choice of features. For this model that we built here, I worked with Eva Holtz and with the help of Katrin Kirchhoff, and we came up with a set of 8 multi-valued features with a state space size of about 9,000. And Eva will talk more about the particular choice of features. Okay, so there are issues with model size and constraints. So these models can get very large. So you want to use interframe constraints, which we've already put in, and interarticulator constraints, which we haven't put in, which is why they're light purple, to limit the size of the state space. Otherwise, you get an explosion. And what we did do in this workshop, which I thought was really nice, was we experimented with varying the size of the state space. So Eva made up these tables of probabilities that we could initialize the models with, and basically we would put different thresholds on these probabilities, and we could play with smaller models, larger models, etc. Initialization is a big issue for articulatory models because you can't start with a flat start. There's no way for EM to figure out which articulator corresponds to what when you start with a flat start. So we started by initializing from existing phone models. When multiple phones match the same feature configuration, we'd like to aggregate the models, and that's dark purple because that's been begun but not completed. And if no phone at all matches a particular feature setting, we'd like to interpolate from phone models that are close to that feature setting. And that I haven't started to do, but I would like to. And finally, I would like to try some discriminative structure learning over the hidden articulator variables. Okay, so the main points that I guess I want to get across are we think that speech might be better modeled by articulatory features than by phones. We think that graphical models using the GMTK toolkit would be a nice, concise way of expressing articulatory models. And the plan for the work is to start with experiments using the model that I've shown with a pre-specified articulatory structure, and then move on to doing structural learning with the hidden articulatory variables. Thank you.
Most people, when they think of articulatory to observation models, or a lot of people, when they think of relatively nonlinear transformations, one way of achieving this, of course, is just treat everything as a mixture of Gaussians. After all, that's the old thing to do these days anyhow. Is this sort of how you would implement that transformation?
The initial model would be a mixture of Gaussian's model, but we've also discussed using like a product of experts model. So it would allow for greater data sharing, but it's, I don't know, it might be less motivated, I'm not sure. But I'd like to try both.
So I have a question here. Are you assuming that the articulatory, one possibility is to actually get acoustic observations related to the articulatory features? The other is to assume that they are hidden by some or all of the others. So which...
I'm assuming that they're hidden.
That they're hidden.
Yeah.
And are there any indications that, similar to the AMSM model, that indicate that these are actually helpful in this initial experience?
Yeah, so they have been shown to, at least in conjunction with MFCCs, improve recognition. And also in high noise conditions, there have been some results that show that they do better than MFCCs.
But have the dependencies been coded manually? Or
Yes, for all of these dependencies that are being coded manually, I'm hoping that we can get a win out of learning. Okay, thanks.
Okay, hi. I'm Jerry Torres. I'm an undergraduate from Stanford, California. And my work this summer was mostly dealing with language modeling in the graphical model toolkit. So basically building a language model with the graphical model toolkit language. Okay, this is going to be quick. So the first thing you have to do is choose a corpus. And we chose the IBM audiovisual corpus out of the three that we had. It has 13,000 trading utterances and a 13,000 word vocabulary. So it was pretty rich and you could play around with that. And the choice of the language model we chose to use is linear interpolation, which basically takes the higher order n-gram, multiplies it by some fraction, and then adds to it 1 minus that fraction times the lower order. So it's just linearly interpolating those two and doing it recursively until you get to the actual lowest gram. And so this was a simple Jellinek Mercer, and started that back in the day. Okay, so the GMTK implementation. Now we ran into a couple issues when we wanted to implement it in the graphical model toolkit. First of all, the graphical model toolkit keeps track of the word at every time frame. But it also keeps track of the pronunciation variant with that word. Say, for instance, the and the. Our model is the 01 and the 02. And we just want to condition the language model on the word. Another thing was also the word variable at each time frame also kept track of silence. And we didn't want to condition the language model on silence. So this created an issue of we don't want to just look at the past word because it could be a silence. So we might have to look, back arbitrarily far to the last real word. Now this creates the need for a new variable. So we have to implement that in the structure. So I'll show you that next. So here's the structure. And this is a bigram structure, basically looking only at the last word, and it's interpolating between the bigram and the unigram by this fraction alpha. Okay, so this is the all familiar decoding structure, everything below this line in this box. And that was what originally was used for decoding. And what we need to add was that new history variable. So this is the last row word variable. And the last row word variable will just copy the pronunciation variant, stripping out the number at the end, so we won't, distinguish between the different pronunciation variants. And we will also not copy it if there's a silence, because we don't want to have silence as the history. And then, so this last word is going to condition, it's going to be a switching parent on alpha, which is interpolation fraction. And depending on what the last word was, we can choose a different fraction to interpolate the two higher gram and lower gram. So that's the basic structure for that. And analogously, we're able to do a trigram model by just adding another variable for the last word and adding another variable for interpolating the trigram and the bigram. So this will pop up right there. So here's the last word. Here's the interpolation fraction, and that's what interpolates the trigram and the bigram. So that's the basics of it, and we're able to run some tests. So here's first a simple experiment on how that results using the bigram model. First of all, here we can look at alpha, which is the interpolation fraction between the bigram and the unigram, and the perplexity. It's graphed as the z-axis. And also this other issue of having a cutoff. So this cutoff is defined as if the history has been seen less than this cutoff, less times than this cutoff, we're just going to go exclusively to the unigram by making alpha 0, which would make this 1. And that has shown gains in trigram language models by using a cutoff of 1. And we're just wondering if maybe it'll work for bigram. But in the case of audiovisual data with our language model, we found that the best cutoff was 1, meaning just go to the unigram if you haven't seen history at all. And alpha should be relatively high, about 0.9 is the optimal value for that. So that's some of the results for the held out data. And then we ran on the test data after training the parameters. So here's the test data results. This is kind of small. Here's a bigram language model and the trigram language model, perplexity on the side. And basically what this is showing is we're using the bigram language model, training the parameters on the held out data, and getting complexities for 1 bucket, 2 buckets, and 10 buckets. And these buckets are basically different values of alpha that we can use. And those depend on how many times we've seen the history. So we can vary the type of alpha that's being used depending on how many times we've seen history, which is just standard stuff. So for 1 bucket, you can see a complexity of 89, and then a significant gain for just adding another bucket, meaning when you have 0 or alpha. So that was the results that we just showed the graph of previously. And also adding more and more buckets really didn't help in this case. And that was probably because we didn't have enough training data, I suppose. And so the trigram showed significant gains, nearly cutting the complexity more than in half. And similar results for adding another bucket or adding multiple buckets. Okay. And so finally, we're talking about here future applications. One of the future applications is higher order n-grams, which would simply be meaning adding an extra variable on top of this dude right there. Skipping models. Skipping models basically are ignoring some of the history words, which were what we were kind of doing when we ignored silence previously. So skipping models is another idea. Caching. You can also cache and use variables for memory at each time frame. And also sentence mixture models. And sentence mixture models basically change between different language models based on the type of sentence that you see. So sentence type can be a hidden variable in the structure, and we can condition on that. And that's it. Oh, there's some questions.
Hi, I'm Eva, and this is going to be somewhat brief because I'm only allowed 5 minutes. All right, so to follow up on Karen's talk, how to go about choosing articulatory features. Well, here are 3 concerns that we have. One is that we need local cardinality because having a as small a state space as possible is important both in training and decoding. But at the same time, we want that every configuration of feature values assigned to a phone should make it unique from all the other phones, ideally. It doesn't necessarily have to be the case, but if, for instance, P and B have the same values assigned to it, then you have to rely on your language model to say, like, oh, it could be Paul, it could be Ball. It's probably Ball because you don't use the word Paul much. Lastly, it's nice if you don't have to hand add additional constraints to articulatory features. It's not crucial, but one feature set that we've seen, I believe they had to specify by hand that the backness of the tongue tip could not be more back than the backness of the tongue back, something to that effect. So these are our articulatory features. Again, not much time to go into them, but a couple comments. First of all, again, many thanks to Captain Kirchhoff for her help in making these, as well as Karen. Secondly, we're pretty happy with these features because they make almost all phone states exclusive of one another in terms of the feature value assignments, with the possible exceptions of the end of certain diphthongs. For instance, the features assigned to the end of I, I'm pretty sure is the same as the end of A. Okay, this is maybe a little complicated. This relates to, if you recall, these. Again, these are where those three pretty pictures are these things here, and I'm going to use an analogy to try to explain what these panels are, because it took me a while to understand. Imagine somebody walks up to you and hands you a loaf of Wonder Bread, and he or she says, okay, this loaf of Wonder Bread has 3 dimensions, height, width, and depth. And he says, the Wonder Bread is moldy. There's mold distributed throughout the Wonder Bread. And I have 3 questions for you. The first is, which height and width coordinates on average have the most mold? Which width and depth coordinates on average have the most mold? And which height and depth, coordinates have the most mold on average? And so what you can do in a slightly parallel universe, but not just close enough you can imagine it, is if you want to know which height and width coordinates have the most mold, take it, smash it, until basically the mold has packed up, and you have this like single two-dimensional, essentially two-dimensional slice of bread, and you can see, oh yes, like right here we have lots of mold, and right here we have lots of mold, and here we have very little. And so, what does this have to do with mutual information? Well, mutual information is also a three-dimensional system where your 3 coordinates, rather than being height, width, and depth, are the child number, the child feature number from, in most of our experiments, from 0 to 41. The parent feature number, I'm sorry, I is for index. So the parent feature number, again, often from 0 to 41. And then the time lag, which I guess went up to negative 150 milliseconds. And so, by squishing the bread in 3 different directions, we can get the mutual information, rather than mold, between the child number and parent number, averaging over all lags. We can get the mutual information between the child number and the lag, averaged over all parents, and mutual information between the parent number and the lag, averaged over all children. And so this is what they look like. As you encountered before, lag versus parent and lag versus child are fairly similar. And then parent versus child is fairly symmetrical. And a few quick observations. As Jeff mentioned before, yes, this is near 150 millisecond time lag, and there does seem to be discriminative, plenty of discriminative mutual information there, so that's interesting to look at. And another thing that's sort of interesting is that there's not a ton of visual information here, but it's along here. And, well, I'll give you this in a second, but along here is where the child feature and the parent feature are the same. And it sort of makes sense that they should share something. And then also it's kind of interesting because these are the builders. And so, of course, child feature 15 shares something more than the typical amount of visual information with its derivative, for instance. So that's what I think is key.
Are there any general questions for the Jeff and Jeff group? This is a short open discussion kind of thing. No, in that case, let's have a big round. Go ahead, Dave.
No, I'll take off.
No? Okay, all right. Let's give both the teams a big round of applause. I have a couple of concluding remarks, but before I do that, I'll offer the floor to Charles Wayne in case he wants to say something, and then Jim Bass wants to also tell us a few things. So,
Well, I have very little to say, except that I was very pleased to be here today and see all of the work that's happened both this morning and this afternoon. So I congratulate you for what you've accomplished. And I look forward to seeing the reports. They're going to come out with it. I know this will take a while to get it all down on paper, but certainly started with good things. And I'm just very happy. So I thank you very much. I hope we can do this again next year.
Well, I've learned that mutual information is mold. I like that. I'll take that with me to the day I die. In addition to saying thanks for a great job on both the projects, I'm going to go ahead and take this opportunity to announce that I've had a BAA approved for distribution. It should go out next week for an ASR program. And I had selected this venue to go ahead and make my first open discussion about it. There will be a website for it, of course. Do that to the folks. How's that? I find that wasn't too good. All right, very good. Everybody all right? Okay. People have been a little confused about my projects because I've had, we've gone through names like ROAR and all kinds of interesting names. This is one of, as I like to call it, this is a part of the ROAR pride. How's that? We've decided to split the program, ROAR itself, into 3 different programs to make it more manageable, also make it easier to get it approved. And it turns out the sum of the 3 individual projects were greater than if I had done it as a single project. That took some thinking, so we've done it. And the first one we're going to do is spine. And of course, spine is a term you've already been hearing because some people have been, NRL had started a speech and noise environment, so what it stands for, had started a evaluation program that had a challenge task. Well, I've decided to take that task and turn it into a multi-year program. It has 2 fundamental tasks. First task is tech-based, in which some of the things I've even heard today, these represent projects that do not necessarily have to be tied to a system or to a full functional ASR engine. So if you're interested in doing research in a particular aspect of ASR under one of these or other categories, this is your opportunity to get a nice multi-year program under your belt so that you can have some consistent funding. The last one, even though it's only 1 bullet, is actually the major thing we're going to do, and that is, of course, I am also soliciting organizations to build end-to-end systems to continue doing the spine challenge. The interesting thing about the spine challenge is that it's going to reinvent itself. Spine 1 was done strictly by NRL. Spine 2, the one that's going on right now, we picked up the funding for it, and the additional spines that we do from now on will have subjects that are going to be shaken, rattled, rolled, put into vehicles, etc. So there will be more aspects and more flavor to the, quote, noise and to the speaker stress. So we're really starting, just when everybody gets comfortable solving a particular problem, we raise the bar. Well, we're just about to raise it a pretty good amount. But this will also enable these other aspects of ASR to shine. That's the whole point. These are other goodies that I think people, if you work in these areas, if you're familiar with people who work in these areas and you'd like to work with them, I'm very much into collaboration and to teams. I like to see academic and industrial components get together. I like to see small industries team up to add aspects of various new avenues of speech work. All right, guys, here's what, if you're going to do the basic research, if you're going to work on one of these components, make sure you're meeting this criteria. Don't make me a liar. This is what I told Congress you will do. You will do far-sighted, high-payoff research that provides the basis for technological progress. Right? Good stuff, right? Just basic stuff. I'm going to be very quick here. I don't want to take a lot of time. All right. I'm not going to read these. I'm going to give you just a couple of seconds to take a peek at it, and I'll probably highlight something. But there are 5 big areas I'm looking for. Maybe that's all right. Kind of go off this. All right. Multidimensional signal processing. You can see, I know everybody's quickly looking to see if my area is in there. I know that, and that's why I'm doing this intentionally. Acoustic modeling. My West Coast people tend to like reciprocity. Recognition approaches.
Jim, I presume these oils are going to be on the webpage.
They will eventually be on the website, yeah. Because I'm presenting them here, they are now everybody's, and you can call, oh, by the way, we've changed the old wives' tale is dead. You may call me and ask questions during the period of time the BEA is open. Good Lord, does that mean I'll get an unfair advantage? Well, call me. If you don't call me, you apparently don't get an unfair advantage. The lawyers have said it's okay. There are some specific questions I will not respond to, but you may ask. Okay, don't ask me how much money you can get, right? But I can give you a level of effort that will help you scope it to have a reasonable chance of success. That was one of the big problems. Do I ask for $1 million or I ask for $500,000? And if I'm wrong, am I taken out of the competition just because I got the amount wrong? Well, the answer with me was no, because all I do is approve it and then negotiate it to the proper scale, right? But nonetheless, we want people to have a fair, get an idea of what you can get. And linguistic support. So all you language model guys and gals, get ready. All right? It's going to be out for 55 days. So when it's out, you have 55 days to read it, and you have that same 55 days to write the proposal. When you go to the website to pull up the full BA, you can read it. There's also a little help guide called a PIP, which tells you how to write it. Right? Very easy, very simple. I wish you all good luck on it, and give me some good ideas. And that's it. I don't know how to turn that on. Okay.
Thank you. Any of the others? Jeff?
A couple of random slides and then we get on our way. One of the big successes of the same workshop is that every teacher watched their coffee cup. I don't know, those of you who remember from past workshops, that used to be one of our complaints.
And this here we should put down all right. Yep. Okay, so that's where I left you this morning. So that's where we start. So we've heard from 2 groups. They've done a lot of very good work, worked really hard, pretty much starting January of this year. And if you plot the intensity of effort, it goes up something like that. And you should, like many of you said earlier today, or some of you didn't admit, they've been working pretty much 48 hours at a stretch now. So what did they achieve? Well, these are my impressions, by the way, based on their conclusion slide. One of the things I thought was very interesting about Drago's summarization effort was that they found this really difficult measure of co-selection. It seems like people seem to don't agree on co-selection. So it's not like if I give you a 100-word, 100-sentence document, you and somebody else will come to the same top 10 sentences. But on the other hand, if you look at how important you consider a sentence and you start looking at other measures, there seems to be much more agreement. And I'm just putting up relative utility as one measure, but many of these sort of content-based measures seem to be at least having human agreement, and I feel that this is therefore a good thing, and we'll eventually be able to look at quantitative evaluation of summaries, which right now seems to be pretty elusive. This was the impression I got out of it. And hopefully the people, nobody's standing up and yelling at me, so I'm assuming that either they agree with me or they're dog tired and don't want to hear anything. I hope it's the former. Of course, they did a lot of other interesting things. They looked at query-based summaries as opposed to generic. They looked at comparing manual extracts versus abstracts, and this goes to one of Michael West's questions, like, are the two even comparable? Isn't there a big argument? Well, here is a corpus on which you can actually study both and sort of start looking at what the differences are and whether it makes sense to go after one or the other. One of the other big achievements of this group is more in terms of resources. I think they developed a really nice toolkit. I've seen it. I haven't actually used it because I've been doing other things the last few days. But it's looking nice. I've seen them turn around a new feature. I think 2 years ago we said machine translation in 24 hours, and this time I think it's new feature and summarization in 24 minutes. So I think they were able to put a new feature, build a summarizer, test it all in half an hour. And of course, the other tricky part is the evaluation of summaries, and there's a lot of progress in that direction. And finally, there was this annotated corpus, hundreds of documents, summaries of clusters, extracts, and when I say summaries, I mean both extracts and abstracts. And I'm sure this is going to lead to a lot of research in the future, and it's going to basically be a launch pad for all sorts of good results. And hopefully, people will see the value of this, not today, but 5 years from today. The graphical modeling group, again, produced a very valuable resource. What I like about the graphical model toolkit is that I'm sure it's going to be used for things other than speech recognition. And I think that's where it's really valuable. It's a very powerful general purpose toolkit. And unlike some of the things that are developed by people doing machine learning and working with the UC Irvine database, this is heavy duty stuff. This can take 5 million examples for training with 650 class labels and actually run with it. It's not binary classification with 1,000 training and 50 test examples. So this is a real thing. And the reason I believe it is because it's been tested in all these corpora. And then, of course, about the actual research, I found that, confusing as these pictures might be, they actually tell us a lot about what's going on in our system. And it's telling us where the current HMM systems are perhaps lacking, where perhaps there is progress to be made, where the mold might be. So, and we started improving the word error rate. So again, I expect to see lots of good things in the future. And I have nothing to do with any of these accomplishments. All these people in this room are. So again, my turn to clap. There are a couple of other people we need to clap for who I don't think are here, but I must mention their name. These are people who really make the workshop work. Laura, who some of you have met, most of you have heard from, and her two assistants, Aaron Sachs, who was here earlier this morning, and Smita Rahman, and of course Jacob Latterman and his team of computer assistants, Ashima Munjal, Pen Fei Sheng, and Matt Marsh, our webmaster. And these people, of course, deserve a lot of credit for keeping everything running while we go do our goofy stuff. So again, let's clap to them. one of those things, if a tree falls in the forest. Actually, I had a better example of it. The question, if a man says something in a forest and there's no woman there to hear him, is he still wrong? But anyway, with that, let me conclude. Dinner at 7 o'clock. Everybody's invited. It's out in Decker Gardens. I think it's time to have fun.